Okay, we have one more application to get through, and it is that of electric circuits. It's something that might appear pretty intimidating. I know that myself, I wasn't the great. I came to the University of Guelph as a physics student, and I changed to math exactly because of some challenges that I had with electricity and magnetism courses. So teaching this stuff was super intimidating for me too, but overall, it's really not that bad. I'm going to take you through it pretty carefully, and even if you have no science or physics background at all, you should have the tools that you need to be able to put together the equations that can describe these things. Okay, so don't be stressed out. We're going to take a look at it together step by step. So, differential equations can be used to model an electric circuit that contains resistors, inductors, and capacitors. These are different kinds of objects that can appear within a circuit, different components that do different things to an electrical current. For this, right, this isn't a physics or electronics or any, this is a math course. So really we're servicing and showing how differential equations can arise from a scenario. So if you want to know more about those things, go ask your other professors. But I'll give you just enough to put together these models. For any differential equation, though, we know that we need a dependent variable. So what should the dependent variable be for a differential equation like this? Well, if the independent variable represents time, the dependent variable could be a few different things. The three things that I will expect from you, and I'm not going to go too far outside of the kinds of examples we do here in this video lecture, but you could measure the charge in the capacitor. Usually it's denoted Q of t, and we measure that in coulombs. Don't worry about units very much either, because as we set them up, you shouldn't have to do any manipulations or conversions or anything like that. I will make sure that things are in a non-stressful format where you don't have to do anything but manipulate some numbers, okay? You could have a dependent variable that's the flow of electric current, I of t. I of t is the flow of current, it's the change in the charge over time. And so you can actually express I of t as dq dt. These are similar, and we're going to be converting between the two. That's one thing that I want you to keep in mind as we go forward, that I is nothing more than the derivative of q with respect to time. If we want to set up a differential equation in one versus another, keep that relationship in mind and it won't be bad. Electric current is measured in amperes. And the other possibility, and it's a little bit of a different situation that people tend to use and set up differential equation models with, is the electric potential difference in volts across a capacitor. We're going to do that for, I think, the second example that we get into. And setting up a differential equation is slightly more involved with that, but we will go through it step by step. One nice thing is that there's only so many kinds of differential equations that can arise from these things, and every single one of them that we will tackle is linear. So the solution method's no problem. It's just really taking the time to make sure that you understand how to set that up. Okay, yeah, all of these different things have units of their own. Again, don't get too excited, but in case you want to flex your physics muscle, resistance is in ohms, inductance is in henries, and I think it's like, I forget if it's, I'm going to say IES here, it might be YS, I'm not really sure. And finally, we have the capacitance, which is in farads. And these are all going to be positive constants that appear in the differential equations, nothing but that. So there are some restrictions in play here that come automatically. Okay, from fundamental electricity laws, any of these components could appear in a circuit. And so you'll get to know these things. They appear graphically represented in particular ways. Excuse me. The voltage drop across a resistor. If you see a resistor, it's going to look like this, which I affectionately like to call Mr. Jaggy. And because, I don't know, it's Jaggy, I guess. And it comes with a voltage drop that's associated with it. It's a term that's going to appear in our differential equation. The R is a constant, so don't freak out about that too much. The I is that current from before. And if you see one of these resistors, you're going to have this VR term that appears, I times R. Okay, that component may or may not appear. Across a capacitor, you're going to have something else, a different symbol. That symbol kind of looks like two, I don't know, like lines like this. You know, it looks like, I call it Mr. Squishy because it looks like somebody, you're about to squish a bug, like, I don't know, but that's not what it does. It's a capacitor, and it has a couple of different forms. It's the charge over the capacitance, which is this form right here. Or you could write this, thinking back to what that the relationship between current and charge, you can also express it in the form of an integral. And we're going to use both of these at some point going forward. Don't be too worried about the tau. That's just a dummy variable inside. You could put whatever you want here, depending on the situation. But it is integrated between whatever the initial time is and the current time to make sure that this here is nothing more than a function of t at the end of the day. Okay, the last thing is an inductor. And the inductor is a component that is L, the inductance, a constant, times the change in current with time. And so this is the third formula, and it's associated with Mr. Squiggles. I always forget how many there are. There's one time when I in the first times that I offered this stuff in the course, which was at popular demand because students wanted to get more practice with basic circuits, and I don't know, I wasn't very experienced, and I think I had a Mr. Jaggy with like 5 different jegs because I didn't really realize, and like I remember getting a talking to from an engineering professor because they were unhappy with my number of Jaggy spikes. So I guess this is really important. I'm ignorant. I'm just a math guy. I put together differential equations and I solve them. So I will try my best to have the right number of spikes and so on. All I really care about from you is, can you put together the differential equation? So those are the different kinds of drops that we can have. They're different components that appear in a circuit that will help to kind of craft the differential equation model. But to go with that, you could have what are called voltage rises or sources. And typically, these are going to be like batteries in your circuits, or maybe something that generates voltage. So the voltage provided by such a source can be a function. So you can have a battery that's got a generally constant supply, or you could have, say, some sort of source that decreases exponentially over time, maybe slowly, maybe quickly. You could even have something that's like a sinusoid to represent, I don't know, something like a solar battery or something like that that might vary by the day or by the season. So these are different kinds of things that can appear in the surface that provides the voltage, and then the different components that appear are the drops. And to put this together, we use something called KVL, which is this guy's voltage law. I say this guy's because I did a quick search. I was like, oh, if this is going to go on to YouTube and be public and so on, then I better be pronouncing his name right. And it doesn't seem like there's any great agreement if it's Kirchhoff or if it's Kirchhoff or if it's like Kirchhoff or something. I have no idea. So it's this guy's voltage law, and with the greatest respect, way smarter than I am, I'm sure. You can call it whatever you like. Okay, I don't even know if there's 2 H's here or not. I think there is. It's either 1 or 2, so I apologize if I got it wrong. All right, anyway, this law, KVL, which we'll call it, in that case we can't screw it up at all, what it says is that the sum of the electrical potential differences around any loop is 0. And that's going to be the rule that we use to construct all of the circuits in this course. In other courses, things could get more complicated where you could have like a parallel circuit or different kinds of setups that go beyond simple loops. So all we're trying to do here is showcase some of the basics and the behavior that leads to. So we have 3 examples that we're going to go into, and we will work through them. I'll provide a full solution to the first one, and we will talk about the other 2 to try and make sure that they're set up. But here it is. So it looks a little bit intimidating. This thing is scary for some people, but I promise you, right? Every piece of information you need is right here, and the units will work out perfectly, I promise. So let's identify some stuff. We have a circuit, and it has resistance of 50 ohms. So R is equal to 50. We have an inductance of L equals 1 Henry, so L is equal to 1. See, I think I used one more loop here. Oops, so one of them is wrong. And a battery that applies a voltage E of a constant 5 volts. So this here is 5. So it's a small little battery, it looks like. At time equals 0, the switch is closed. So at that very instant, we assume there's no initial current. That's going to let us assume some simple initial condition, which is going to be, let's see. Let's look at part A. It says construct an IVP that models the situation with the current I of t as the independent variable. So if there's no initial current, our initial condition is going to be I of 0 equals 0. Okay, we're going to construct an IVP that models the situation with I of t as the dependent variable. Here's how it's going to work. I'm going to look through this circuit for all the different rises and drops and construct an equation based on that. So it looks like I have a resistor and I have an inductor. So those are the two drops that I'm going to have. And so if I look, I have, there's the VL, this is from the inductor, and here's VR, this is from the resistor. The E of t, that's from our battery, and the sum of the rises has to be equal to the sum of the drops, and that's exactly how we get here. Okay, so with that, I'm simply going to sub in to what we have using those formulas in the last page. So VL was equal to L times di dt. VR was equal to R times I. I think I wrote IR on the last page, but whatever. And E of t is E of t. And I have all the values here. L was 1, R was, I believe it was 50, yep. And the E of t was simply 5. So we get di by dt plus 50I equals 5. And it looks like our initial condition we wrote before was I of 0 equals 0. And bingo, just like that, we have an initial value problem. No problem, right? If you know the components and you know the formulas that are associated with them, then putting together a differential equation like this is really no problem at all. Okay, so don't stress about it. It's just a matter of remembering those different pieces of the puzzle. Okay, so let's see. Oh, look at that. On the next line, I said our initial condition is given in the problem, I of 0 equals 0. So we're going to work with that. And all we're going to do is solve this thing. And let's see. We have di by dt plus 50I equals 5. And you stare at this for a second, and heck, it's a linear equation. My di dt and my I appear in separate terms. There are only constants involved otherwise. So in fact, it's a pretty easy and straightforward kind of linear equation. So no stress, this should be review. We need an integrating factor. And that integrating factor is e to the integral of the 50 dt. So there's no problem at all. This is going to be an e to the 50t plus c. The c can come down. Choose c to be what you want. You get e to the 50t. Choosing c. I'm really skipping steps now, but I guess I'll write it. It's hard to say choosing c appropriately when I don't have a c written down anywhere on the page. So something like this. And simple integrating factor. And I'm going to take that and do the usual steps for linear equations. So multiply through. You know, you say, I'm doing a circuit, this is stressful or whatever. But no, it's just solving a linear equation. So don't let that freak you out. E to the 50t di dt plus 50 e to the 50t. You can see the product rule there perfectly. and then equals 5 times e to the 50t. Product rule backwards. Same as usual. This is almost sad. This is one of our last examples that we'll go through completely with first order equations. So, you know, we've come a long way. E to the 50t times I, all prime, is equal to 5 e to the 50t. We will want to integrate. And if we integrate, there aren't any hard functions here, right? It's just what it is. E to the 50t times I equals the integral of this. 50 has to be adjusted for, so I get 5 over 50, which is 1 over 10. E to the 50t plus a constant. And finally, we want to isolate, of course. So I'm going to divide both sides by e to the 50t, or equivalently, multiplying both sides by e to the minus 50t. And we get I equals, well, look at that. We get 1/10, and then we get c e to the minus 50t, just like that. That is our general solution. It's a general solution, but we did have an initial value problem, so we would like to apply that now as a last step. But that's even simple as well. We had that I of 0 is equal to 0. So that was I of 0 equals 0. Let's plug that in and see what happens. So I get I of 0 equals 0 equals 1 over 10 plus c e to the minus 50 times the 0. E to the 0 is 1. And so it looks like we're simply going to get that c is equal to, bring that over, minus 1/10. So just like that, we have a solution to our initial value problem. So a solution, or the solution I'm going to say, the solution to the initial value problem is going to be I of t equals, same thing as we got before, but now with the c plugged in here, minus 1/10 e to the negative 50t. So it's kind of interesting. If you take a look, it should make some sense as well. We know that this function here, this I of t, should satisfy the initial condition. And of course, when you plug in t equals 0, you get a 10th minus a 10th, which is that 0. But you're going to find that as t goes on, that exponential, well, it's going to get smaller and smaller and smaller, and you're subtracting off less and less and less. And pretty quickly, that solution is going to approach 1/10. So it starts at 0, and then it's going to blast pretty quickly. You could graph this function if you wanted to, and it's going to asymptotically approach 1/10 as t marches on. So this is our first problem, and that's one setup. Now, it was a pretty simple setup, and so I wanted to show you a couple of different situations. I said there could be 3 different possibilities for this course with how you set up these differential equations for circuits. One of them was with the current, and that one tends to be fairly straightforward. Another one is going to be with setting up a differential equation so that Vc, that voltage drop across the capacitor, is itself the dependent variable. That's a little bit more complicated. That's what we're going to do in the next example here. So we have a circuit diagram here, and let's go through and kind of do the same thing. We're going to label some stuff to start, but then kind of discuss what we'll do differently this time. So we have a slightly different voltage this time. It's an exponential. That's not going to be a huge deal. E to the minus 1 over 100t. We have a resistance that is 80. And we have a capacitance, C, which is going to be 1 over 400. All right. So far so good. I'm just kind of applying the different information in this problem to the drawing of this circuit to try and match up different components and so on. So that's fine. But this time, the question is asking to model this situation with the voltage across the capacitor Vc of t as the dependent variable. In the last example, if you go back and see yourself, it was the current that was the dependent variable. So I'm asking you to model a fundamentally different thing. That means you have to set up your differential equation in a fundamentally different way. It's still drawing on the different kinds of components. We're still going to be working with those things, but we have a different quantity as the dependent variable. So read these problems carefully to see what is being asked, and then design your models accordingly, okay? And this time too, there's an arbitrary initial voltage given by, something at time 0, the initial voltage is equal to whatever it is, V0, some constant. So I'm going to say here that this is some constant. And I might pose a problem to you that way as well, and have you set things up in terms of a parameter of some sort. Okay, so let's see. We have to consider the different kinds of voltage drop. So we had a resistor this time, right here, and we had a capacitor this time. Now, notice that I used the integral form of this instead of the form that I used in the last example. I guess I didn't use the capacitance in the last example. That's okay. We had two different forms for the voltage drop associated with the capacitor. And one of them was this Q over C, and the other one expressed the Q as this integral. And I've put that right here. The reason that I'm kind of drawing on this integral form right now is because I'm going to need to express the VR in terms of VC. I need everything at the end of the day to be in terms of VC for this example, because I'm setting that up with that being the dependent variable. And because both of these quantities, the VR and the VC here, have I in them, that will let me relate the two and write one in terms of the other. So hopefully that makes sense. We're going to go through some steps together and you'll see how that works. Okay, so that's exactly what that next sentence is saying. And here's what I'm going to do. Right now that I is trapped inside an integral, but as I said, you could take a derivative, I said before, to get a related quantity. So let's do that. I'm going to take the derivative of that second formula right there. And if you do, it's pretty straightforward. Imagine that whatever this integral is, I'm subbing in a t at the end of the day, and if I take the derivative of that quantity with respect to t, I get back the I as a function of t. So as a matter of fact, it's pretty straightforward here. I'm going to get dvc by dt is 1 over c times I of t. And if you compare that to the integral on the last page, I mean, it's not that hard to get here, just using, what you know about fundamental theorem of calculus and some intuition. When it's like this, I can isolate for the current, okay. And I get I equals C times that derivative. Okay. So that means that I can take this, and I said I wanted to write the VR in terms of the VC here. And my VR was equal to I times R. And I can take my I here, and I can plug it in right there. And I'm going to get this. I have a constant, I'll write those out front maybe. So maybe I'll write RC. And then the I here is going to really just be the C that I just wrote times dVC by dt. So essentially, the reason I'm going through all of this is because, well, I have VC, but now I have an expression for VR that's in terms of VC. And I can write both of them down into our voltage law and get to an expression that involves a differential equation that I can then go solve. So the differential equation here, VR, VC, those are our drops. E of t, that battery, is our source, our voltage rise. And if I equate the two, I can plug in what I know for each one of them. So it looks like VR, we determined, was RC times that derivative of the voltage drop across the capacitor. VC is just VC, so that's great. I want a differential equation in terms of this, so I'm going to leave that alone. E of t was, oh gosh, what was it? It was some exponential. It was e to the minus 1 over 100t. E to the minus 1 over 100t. So that's what we've got. Our initial condition we said was some arbitrary initial condition given by v of 0 equals v naught, whatever that is. And you can set this up. The r and the c we know. We've got that battery on the right, and this will lead to yet another differential equation that you can solve. I've left that for you to try because it's yet another linear differential equation. This is good practice. This is the solution that you can get to, and you should try that to make sure that you're solid with that. But the difference here is in the setup, and that's what I wanted to go through a little bit carefully. Now, one thing I do want to say is that you can just memorize the way that like what kind of differential equation this leads to in this situation. But I find that it's helpful to keep those rules in mind and just be able to derive it on the fly. I've done that since the start when I retaught myself all of this stuff. And to me, that makes me stronger. So I definitely recommend that you do the same thing, that you go through these steps, make sure you understand those steps, because it will serve you well, especially when we get to some concepts later in the course. Okay, so try that differential equation, try to solve it on your own. This is what you should get to, and you'll notice that the final answer does depend on V0, that initial, the initial voltage, the V0, right? Because without a number there, I need something to be there that's in terms of that number. Anyway, because we don't have a specific constant as an initial condition, we can't have a specific constant in the final answer, and so that's why that's there, is what I'm trying to say, awkwardly. Okay, one more example to go, and it's to kind of cover that third case. And so we're going to set it up here. This one's interesting because you'll notice that it's a circuit that involves all three kinds of drops. We have an inductor, we have a resistor, we have a capacitor, and we have, of course, some sort of voltage. Here it looks like some sinusoid. Okay, let's fill in the rest of what we know. We have that L here is 0.5, taking a look at what's in the problem. The resistance, a great game, by the way. If you haven't played it, it was the original Among Us. I highly recommend. R equals 40. And the capacitance here is 1 over 1,000. All right. As I said, we have this source, which is a 10 sine of pi t. And we have all of the stuff that we need. This time is that last case where we are going to model the situation with the charge in the capacitor, Q of t, as the dependent variable. Okay, so when you're asked to set up a differential equation in terms of the Q, it's actually not bad. Let me take you through it. I didn't use a structure of a note here, or of notes here, so that I could kind of just do it on the fly. It's really not so bad. I have all three components: the L, the R, the C, and the source. So I've got all three of those things. I just have to remember what kinds of formulas are associated with that, and then we'll be okay. So the L was L di dt. The R was R times I. Vc. Okay, we're working with the charge Q of t as the dependent variable, so I'm going to use the formula for Vc that uses exactly the charge. So that's Q over C. E of t is on the right. Okay, you take a look at this thing and maybe you freak out a little bit because I see Q's and I see I's, and we need everything in terms of Q. So we talked about this at the very start of this, this lecture, but there's actually a really useful relationship between the Q and the I. And if you remember, I is always just the derivative of the Q with respect to time. So as a matter of fact, that's going to open things wide up. It's not bad at all. We got a little streak here. I'm just going to touch this up. And yeah, so we're going to use that relationship in order to convert the I's into Q's. So I'm going to say recall that I is equal to dq by dt. And therefore, if I want an expression for di dt, I just have to take the t derivative of both sides. That doesn't look especially complicated, but I'm going to get di dt is equal to, it's the second derivative of q with respect to t. And then I can take this and I can plug in to what we have here. So let's see here. L was 0.5. Maybe I'll plug those in at the same time. It's going to be 0.5. di dt is really the second derivative of the charge. My r is 40 here. The I is the derivative of the charge with respect to time. And then q over c. C was 1 over 1,000 here. So 1 over that is going to be 1,000 q. And then that sine function. So 10 sine of pi t right here. We said arbitrary initial charge, so q of 0 is equal to whatever it is, some constant. And this here is the initial value problem. All right. And so you think about it for a second. You're like, gosh, we should try solving this thing. And then you suddenly run into something. You look at it, and there's a q, and there's a derivative of q, but there's also a second derivative of q. This differential equation is second order, and we don't have a general approach for these yet. I put this example in exactly to show you the necessity of finding solution methods for higher order differential equations. We can set up a circuit just fine using these sorts of tools I talked about in this video. However, we actually don't have the tools yet to be able to actually solve second order equations. So this is the lecture that kind of bridges into the next part of the course, where we start to talk about and build those tools up so that you can solve higher order equations. And so this ends with a great big to be continued, because in a few weeks' time, solving this thing won't be so bad. We're going to have methods for it. It's going to be great. There's a lot of really cool math there, and I'm hopeful that you're going to enjoy the journey as much as I will. So we are about 1/3 the way through the course so far. I hope it's been good so far. Don't be afraid to go back and watch those videos if you need to refresh on any concepts. That concept of linear equations is super helpful for especially a lot of these first order applications. So certainly make sure that you're practicing and getting down those techniques using integrating factors and so on. And finally, I know I say this all the time, but get in touch with me or your TAs if you need any help. And we will be glad to make sure that you are in good hands and well supported. So in the next videos that we touch on, we're going to be into the next chapter where we will start to build up some of those techniques slowly, but we'll get there, to solve higher order equations. So until then, I wish you all well, stay healthy. It's going to be Thanksgiving this weekend for a lot of people, so enjoy that too. And I'll see you in the next one. Bye for now.